All right, so for example 8, we have a disk at the top of an incline. The incline has a height of 10 meters. So that's what I drew over here, that our height is 10 meters. When we let the disk go, the disk begins to slide. And they're asking, what will the velocity be when it reaches the bottom of the incline? And what about halfway down the incline? So that's what I drew up here. So we have to find the velocity at the bottom and the velocity when it's halfway down the incline. So we could use that equation that we derived above, which you should have read about, which is V is the square root of 2gh. And that's just by relating gravitational potential energy and kinetic energy. So this is only going to apply when we're looking at an object that's falling from a height. Okay, so I know that my velocity at the top is 0. So let's find our velocity at the bottom. So our change in height you can think of this as a change in height. So I'm going from 10 to 0, so my change in height is 10. So I can say V equals the square root of 2 times 9.81 times 10. And we end up getting 14.0 meters per second. Now, a mistake that a lot of times we make is we forget to take the square root. Make sure you take the square root of whatever you're multiplying here. So that's our velocity at the bottom. Halfway down the ramp, our height would be 5. So halfway, it would be square root of 2 times 9.81 times 5, which gives us 9.9 meters per second. It's that easy. So again, we can use this formula that we derived, looking at gravitational potential energy and kinetic energy, say that the velocity of something that's falling is square root of 2gh. Okay, this should look familiar. This is a horizontal projectile. And so we're given some information. So we're given the mass. We're told that it's thrown horizontally, our projectile, that the initial velocity is 20 meters per second. But remember, that's the initial velocity in the x direction. And we're told that the cliff is 50 meters tall. So now that's what we're going to call our height is 50 meters. So A is asking, what's the gravitational potential energy of the ball before being thrown? Well, I know that we're at a height of 50 meters. I have the mass, so I can calculate the gravitational potential energy. EG equals mgh. Our mass is 0.140 kilograms. G is 9.81 newtons per kilogram. And our height is 50 meters. So if we calculate that, we get 68.7 joules. So that would be our answer for A. Next, we're asked, what is the kinetic energy in the vertical direction when the ball hits the ground? So we can ignore this initial velocity because this is our horizontal initial velocity. We're only being asked about the vertical direction. So, law of conservation of energy says that our potential energy plus our kinetic energy have to equal the same thing throughout the whole flight of the projectile, okay, because energy is conserved. So I know that in A, my initial velocity in the y direction is 0. So before the ball is thrown, my kinetic energy is 0 in the vertical direction. So I know that EG plus EK is 68.7 plus 0. So this has to be 68.7 joules. When the ball hits the ground, at the ground, my height is 0. And if my height is 0, if h is 0 over here, then my gravitational potential energy is 0. So then I know that the kinetic energy when the ball hits the ground, EK, at the ground has to be 68.7 joules because energy is conserved. All of that potential energy, that gravitational potential energy, is converted to kinetic energy. So if I'm asked the vertical velocity of the ball when it hits the ground, we can ignore this initial velocity over here, but we can do this a couple of different ways. One is we can just say, okay, I know my kinetic energy is 1/2 mv squared. I know when the ball hits the ground, my kinetic energy is 68.7 joules, is equal to 1/2. My mass is 0.14. And I don't know my velocity. So then we can calculate this really quickly. And I get my velocity is 31.3 meters per second. Another thing I can do is I can use the formula from above. V equals square root of 2gh. So if we do V equals the square root of 2 times 9.81 times 50 meters, if you put that in your calculator, you're also going to get 31.3 meters per second. I'm going to really quickly go through the algebra here, how I got 31.3 just in case you need that. And if you want to skip ahead, I'll put a timestamp on it on the next problem. Okay, so here what I did is I multiplied 1/2 times 0.14. So I got 68.7 equals 0.070 v squared. And then I divided 0.07 on both sides. And so I got v squared equals, I'm going to have to check my number. It was 981.43. And then I took the square root of both sides to get v equals 31.3. And I'm rounding these numbers, meters per second. So it's just basic algebra, but there's a couple of steps there. Okay, let's move on to the last problem. All right, a person performs a deadlift exercise, lifting 90 kilogram weights from the ground to a height of 1.12 meters. How much work did the person perform against gravity? What is the gravitational potential energy of the weights after being lifted? And if the weightlifter drops the weights after lifting, what will the velocity of the weights be when they hit the ground? So we have three things we need to answer. We need to find work. We need to find gravitational potential energy. And then we need to find the velocity of the weights when they hit the ground. Okay, so let's take these one at a time. So work is F cosine theta delta x. Now, when you're lifting a deadlift, you're just lifting straight up. So theta is 0, and the cosine of 0 is 1. So we can use work equals F times delta X. So we have to figure out how much work was done against gravity. So that means my work against gravity needs to consider the force of gravity and the displacement. Force of gravity is mg delta x. Our mass was 90 kilograms. G is 9.81. And our displacement is 1.12 meters. So we just multiply those three things together. So 90 times 9.81 times 1.12, and we get 989 joules. Okay, after being lifted, what is the gravitational potential energy of the weights? Eg equals mgh. Now what you should be thinking about is, well, our delta x is our h. So the gravitational potential energy represents the amount of work that was done. So we're going to do this exact same calculation. 90 kilograms, 9.81, 1.12 meters. And so we don't even have to put that in our calculator. It's 989 joules is our gravitational potential energy. So I'll put this was A, if we call this part A, B, and C. Okay, last part. What was the velocity of the weights when they hit the ground? Well, we can use that handy formula we just derived. Velocity is 2gh. Square root of 2, 9.81, and our height was 1.12 meters. So we can do this really fast. And I got 4.69 meters per second. That's it. So once you can reason through these problems become really, really quick and really easy, I think.